Yes? Okay.
by Galen from Microsoft. He's been at Microsoft Research for many years now. He's done a lot of cool stuff in systems and security. Many of the technologies we looked at, isolation, software fault isolation, WebAssembly, he's done related work decades before sometimes. But today he's going to tell you about the latest thing he's been building, an IoT security platform from Microsoft. That's one of the more credible IoT security stories out there.
All right. It's great to be here. I love coming to MIT to give a lecture because I know you're all smart enough that I can just move as fast as I want to. And I'm from southern Utah, by the way, which means I speak at about 5 words per minute. So you'll definitely be able to keep up with everything I say. Please interrupt with questions as you go along. I mean, it's meant to be a lecture, all right? So, and as Nikolai said, yeah, I've been at Microsoft a long time. 3 weeks from now is my 25th anniversary. And as I put it, that either means I've got true grit or a complete lack of creativity and couldn't figure out any place else to go. And you can decide by the time we get done. All right, so I'm going to talk, we're going to do this in 4 phases. Part 1, the problem. Part 2, the product. Part 3, the practice. And Part 4, the proof. I'm going to talk about the product. Clearly, I'm not here to sell you the product, okay, unless you're doing a startup, in which I am. But really, it's a case study of what you can do in terms of security for IoT and what it looks like. So let's start with the problem. Okay, so the problem space that we started out looking at for Azure Sphere are microcontrollers. And you may not have a lot of familiarity with microcontrollers unless you've been in their IEE class. But they are single-chip computers. They've got a processor, they've got storage, they've got RAM, and I/O capabilities all on a single chip. And they're used in billions of devices. They're basically, the way I'll describe it, if you look at something and it has electricity in it, and it has a status light, and you don't immediately recognize it as it being either an Android device or a Windows device, it's got a microcontroller in it, okay? Everything. Home appliances to toys to industrial equipment, up and down the stack. And there are literally 9 billion of these devices, new ones built and deployed every single year, okay? And then there's, another billion devices on top of that that are also embedded, but using larger SOC-type systems. And the problem is, okay, so let's first talk about these embedded companies. And we talk about a deeply embedded device. So we're going to put computation into a device, but we're going to hide it because it's really about the device and about what the device is doing. It's not about exposing a general-purpose compute platform. You're not going to the App Store and loading. I'll give you an example. You're not going to the App Store and loading apps onto your dishwasher, okay? You really just want it to run the dishwasher and maybe even load itself so that because your roommates don't load it is about, what you're trying to get, right? And so if you're the company that builds the dishwasher, you go out and buy a microcontroller and you program it to run the wash cycle of your dishwasher. And you write that code once and you test it and make sure that it actually runs the cycle right. And then you put it in the dishwasher, and then you send the dishwasher out to the customer, out to somebody out in their home or apartment, and you never want to see that dishwasher again. Definitely you never want to have to go debug that dishwasher ever again, okay? And that's the model. And so you don't want anything that happens to that dishwasher that's going to make you have to change the code and go retest the code and everything else. And why? Because you already moved on to doing the next dishwasher. And some of the companies that we talk with that build these embedded devices, there'll be companies that are, hundreds of millions of dollars of revenue, and they'll have like 3 programmers on the device. They've probably got a lot of people on the website, and then they've got 3 people building the dishwasher kind of thing. And that's the mental model. I just want to write this code and put it out there. Well, and the problem is that world is going away. The world where I never have to worry about my device has gone away because of IoT. And think about the dishwasher. Well, one of the things I want to be able to do is I want to make sure that my dishwashers are actually working. And I'll give you actually a better example for this. So this is Starbucks, who are a customer of Azure Sphere. This is their flagship espresso machine. It's called a Mastrano. If you walk into any Starbucks store, you'll find at least 2 of these Mastranos. And okay, confession, I'm from Utah. I don't drink coffee, never have, okay? So these are words I'll admit about espresso. I don't actually know what it means, okay, but, okay, you do. So barista goes, here's the business model. Barista goes to pull in a shot of espresso. Those are the words I'm supposed to use, okay? Pull a shot of espresso, and it doesn't work. You don't get the coffee out of the machine, okay? So what happens? So what happens is the barista calls an 800 number and tech support, Starbucks tech support, and says, hey, our coffee machine's not working, the espresso machine's not working. And they say, dang, that's too bad. We're going to roll a truck. And we send out a truck to repair the espresso machine, okay? And they send these trucks out with very high priority because customers are not happy when they don't get their coffee. People do unhappy things when they don't get the caffeine, etc. And so they run a truck, and it costs at least $300 to roll a truck in North America on their kind of emergency priority, all right? These coffee machines, they have at least 2 of them in every single Starbucks store, and they take on average 6 emergency repair calls per year per espresso machine. Okay, so roughly 6 times in a given year, an espresso machine will have a problem. They have to roll a technician. Now, a third of the time, when the technician gets out there to repair the espresso machine, they go, Doe, there's nothing wrong with this espresso machine. You forgot to empty the coffee grounds, or you forgot to clean the water filter, okay? And the way the VP of Engineering at Starbucks explained it to me, he said, the model you should have is there's a 21-year-old manager and 19-year-old baristas. Guess what? Not the most reliable people on the planet running this, okay? And so mistakes happen. And a third of the time, so 2 of those trips every year are a complete waste of money. They've thrown down the money because somebody forgot to do something obvious, okay? And they went and did a bunch of work and figured out that there was enough data. By the way, these espresso machines pull about 1,200 data points per shot of espresso, okay? They've got sensors all over them. They pull all this data, and what they realized when going and analyzing the logs off the machines is that if we just had live access to the data, we could tell what's wrong with the machine, and we could tell the barista, hey, you just need to clear the water filter, or the machine's overheated, turn it off for 30 minutes and turn it back on, it'll be fine, or whatever else the case was. So they had it. And you do the math, okay? So if we can get rid of 2 calls, 2 truck rolls, $300 times 2 truck rolls times 2 machines times 35,000 Starbucks stores in North America, do the math. Okay, who did it? Oh, come on, you're at MIT. Somebody should have done the math already. It's about $54 million, okay, if I remember my math. Okay, and they said, if we just had connectivity, we could save that much. Okay, really easy for Starbucks to do the math. If they just had connectivity, they could do that. And if you look about any other kind of device manufacturer, they have similar. Home appliances, the failure rate on service calls of, they go out to fix your home appliance and there's not anything really wrong. It's about the same rate. It's about somewhere around a third. It's very, very common in businesses. So there's like this huge optimization you can do, and on and on and on. And of course, Starbucks as well, they could also, they do, allegedly there's this thing, pumpkin spice latte, I think it's called, okay? So there's special recipes that they roll out once a quarter or something like that. Historically, the way they've done that is they load the recipe on a USB key and send somebody out to put USB keys into the machines, okay? And, okay, you guys are security. What can go wrong if you put your proprietary data on a USB key? What could possibly go wrong? Might they disappear, whatever else, right? So there's a question of what could happen to this proprietary information, but also, gee, we'd really like to know that the right recipe got installed on all the machines and the right timeline. So that's another reason why they'd like connectivity. And then there's also just monitoring the quality, making sure that they really are delivering the right quality on every single thing. Because the baristas might not know that espresso's not supposed to taste that way, So they've got lots of really compelling reasons why they'd like to connect these machines. But when we got involved with them, they had never connected them. Okay, and by the way, this machine, you can't see it. It's actually got I think it's somewhere over in here. It actually has an Ethernet port on it. Okay, it was designed by the manufacturer. It's collecting those 1,200 data points. It's designed to be able to output those 1,200 data points. But they don't connect them because imagine what happens on a Monday morning if all 35,000 stores, every single espresso machine is held ransomware. Do you want to be Starbucks that morning? I don't want to be Starbucks that morning, okay? And I don't know what it's like here, but in Seattle, like society just quit, okay? And of course, we've had a good prep for this over the last 2 years, right? So we have an experience what it's like. And so they said, there is no way we are connecting those machines. We can do the math. We know what the value would be, but we won't do it because of the security. And so then we got involved with them. And this is why you care about security on these devices, okay? Azure Sphere, I'll talk about let's see, why did I have this slide in here? Oh, I remember why. So there's all sorts of cloud stuff you want to do with Azure and with your data off your devices, okay? Microsoft has a whole bunch of products, okay? And my team set out to actually just solve one little part of that problem, which is how could you make those devices secure enough that people would dare connect them to the internet? And that they would feel that a company like Starbucks would feel, hey, yeah, our espresso machines are on the internet. It's cool. Okay, how could you do that? That was basically the problem we were trying to solve. And we want to make it for these embedded manufacturers. So for these companies that are building a device and they don't want to ever think about it again. And think about, there's these two fundamentally opposing forces. The one of, I don't want to touch the device again because I can't afford to, because I don't have that kind of engineering capability. And the other one of, I want my device to be securely connected to the internet. Okay, and one of my assertions is that means you have to do updates because new security threats are going to emerge that that nobody even considered when you ship this device, and 5 years later. And so how do we fix that problem? And what we've done is created a product where we basically decided there's 3 pieces you have to have. You have to have a secure root of trust. The hardware has to provide a secure foundation. And we do that. We have a thing called Pluton, which is the hardware root of trust. Have you guys learned about TPMs? Yes? Okay. So think of it as a TPM built, in the simplest case, you just think it's a TPM built into the chip. Well, I'll explain a little bit more detail about it in a minute. That provides a hardware root of trust. And so a manufacturer takes an Azure Sphere chip and they build it into their product. Okay? And then there's an operating system that runs on that chip that provides defense in depth, multiple layers of security, and robust application isolation. And so they build their apps then that run on top of our operating system. And then the device then talks to the Azure Sphere Security Service, which brokers trust, provides updates, and collects error reports. So it provides monitoring of the software integrity on the devices. We don't do the data. So you think about, Starbucks, all that data they wanted to collect. That's all this other stuff in Azure. It's nice sometimes to be able to say, that's somebody else's problem. I don't have to deal with that one. All I have to do is secure the device, okay? And then the final aspect, I talk about Azure Sphere having 4 components. 3 of them are technical. I already described them. And the 4th one is servicing. So we actually maintain the operating system on the device for the customer. So if, let's say there's a crack Wi-Fi vulnerability, we actually fix it in our operating system and we push it out onto their devices, out at Starbucks espresso machines out in the field, and fix them so that they're protected. And so the way I describe, when I talk to customers, CEOs and CIOs, the way I describe it is, you wake up in the morning and you hear, your alarm goes off, or your cell phone goes off really early in the morning, and you look and it's a headline of there's a crack Wi-Fi vulnerability. What do? You roll over and go back to bed because it's Microsoft's problem. And that's basically what we're trying to do. Okay? All right, so let's drill in. Okay, actually, let me pause there. Any questions about IoT, why anybody cares, why security is important? Any of this? Everybody's good. All right. Okay, so let's talk a little bit about the pieces in a little bit more detail. Okay, so first of all, the chip. Okay, Now, what I'm going to talk about today, I'm going to talk about exactly one chip. This is the MediaTek MT3620. It's the first Azure Sphere-based chip, and everything I'm going to talk about here is just going to be in context to that chip. We have other chips that are in progress and some modifications in the platform, but kind of for historical reasons, I'm going to talk about just this product and this incarnation of it. Okay, so it's a fairly high-end microcontroller. So the primary processing core is a Cortex-A7, about 500 megahertz. Think of it, a really slow old cell phone, tiny cell phone. It's got 4 megabytes of RAM, SRAM, 16 megabytes of flash, and a bunch of I/O capabilities, all in a single chip package. If I would have been prepared, it's about this big, okay, about the size of your thumbnail, okay. And there's some things that we put in it to make it an Azure Sphere chip. Okay, so it does have Wi-Fi right on the die. The key thing we add first is the Pluton security subsystem, and I'll drill into that in a minute. But again, it's the hardware root of trust. It provides the secure identity of the device, provides basic crypto operations, does key storage, and is the root for secure boot. And that's probably the most important thing that it does. Okay, and then there are also firewalls. So one of the things we realize is, let's imagine for a minute what you're trying to build is a smart stoplight, okay, traffic light. And if you think about that smart traffic light, there's real-time portions of it, and then there's communications portions of it. Okay, so like on the real-time portion of it, you want the code that makes sure that, when the light goes from green to red, that it doesn't just instantaneously switch. You want to go through yellow and spend some time in yellow. You also want to make sure that only certain green lights are on at the same time. You don't want all directions going simultaneously. And so there's some real-time checks, and typically that's, the tight control code that doesn't trust anything else. We have some real-time cores, these Cortex-M4s, so you can run that code here, and then up on the Cortex-A would be where you'd run the really smart software that's talking with all the other traffic lights and the Department of Transportation and negotiating, how do we optimize traffic flow and a bunch of stuff like that. So kind of think about that mental model. And you want to protect these two pieces. You want them to really act in isolation. And so we have these firewalls. We've put on the data buses firewalls. And and also down at the bottom, there's basically the multiplexed I/O. So think about a single GPIO pin. So the GPIO pin that turns the light green, you want to make sure that GPIO pin is only connected to the right piece of hardware. In particular, only to the Cortex-M that's got the real-time code that's checking the sanity. You don't want a hacker who managed to get into the Cortex-A7 over the network to be able to go turn that light, for example. And so we put separation and put the firewalls in there. And the firewalls they know which core has access to which hardware capability. Think of it as, if you know what an IOMMU is, think of it as basically a distributed IOMMU. Okay? All right, that's the chip. So let's go on to the next step, the operating system. All right, this is my layered diagram of an operating system, and I typically just draw this as a stack, and I realize it might be helpful to put it out so you can see which kind of let's see. So the lower layers are the most trusted, the higher level layers are the least trusted, and then I put the different cores across here. Okay, so let's walk through the pieces of it. So first of all, in the Pluton, so there's a set of operations that Pluton does entirely by itself. In other words, they're implemented in the hardware. I'll give you an example of that. The very beginning of secure boot. So to boot, you always have some ROM that's in the firmware of the chip that does the first part of loading the very first part of the bootloader out of flash and bootstrapping through. Well, we want to make sure that our ROM code hasn't been modified, okay? And so the Pluton fabric has a state machine that's implemented purely in gates that checks the signature on the ROM code, for example, okay? Another example of something that's implemented in the Pluton fabric is attestation. I think I'll come back and talk about attestation in a couple minutes. But all of the mechanisms of attestation, the core mechanism is done entirely in the fabric, and that's so that the keys, the key that you use to sign the attestation certificate, never leaves Pluton and is never accessible by software. So the thing we least trust in the world is software. Okay, and then the farther up the stack you go, the less we trust you from there. So that's the Pluton fabric. The Pluton runtime sits on top of there. It does three core things. One of them is it does the secure boot. So it coordinates turning on the other processor cores within the chip and validating the software before it does so. It does attestation of pulling together the measurements to give to the Pluton fabric to do remote attestation. And it does four things. Okay. It controls access to resources. It's the one that sets up the mappings of the firewall underneath. And the last thing it does is control access to flash for writes. So nothing else in the stack can write data onto flash without the permission of the Pluton runtime. Okay? In particular, like think about your OS image. The OS image can't be modified without going through the Pluton. You can write into a scratch area and say, I've got a new kernel that I want to run. And then you tell the Pluton runtime, hey, would you put this new kernel in the right place? And it goes and validates the kernel and copies it over as it does. Okay. All right, next layer up is a security monitor. Security monitor runs in Trust Zone, the secure world side of ARM. So do you guys know enough about ARM processors? You guys, yeah, okay. So in ARM processors, there's a secure world mode and a normal world mode, and secure world has higher privileges, and basically that's usually where you run more trusted code. So like on your phone, let's see, DRM, your identity stuff, some of the things get stored on the secure world side, and then your apps all run over in normal world where we don't have to trust so much. So we run the security monitor. Security monitor does the rest of resource management, the higher level aspects of resource management mostly. And then we're up to layer 2 of layer 3 of software before we get to the Linux kernel, which means we really don't trust the Linux kernel to do very much other than run apps, okay? And we have a custom Linux kernel. We've modified the kernel to make it more secure and more appropriate for IoT. So for example, if you think about your dishwasher, you never really want to log in as root into your dishwasher, okay? It's not so we've taken out root capability entirely, for example. And then above that are the on-chip cloud services. So this is the certificate management. It's brokering a trust, updates for the device, both for the OS and for the apps, and error reporting. And then above that, we finally get up to where we have the code that is written by the embedded developer to run on their app. And we have the two types of containers. We have the containers that run on Linux, so think of just user mode processes, okay? And then we also have the real-time containers. So I talked about those Cortex-Ms where we can run real-time code. And because of the firewalls and the way we can put the firewall around the Cortex-M, it's effectively, when we manage it and we treat it exactly like it's a user mode process in Linux, only it's off running over on this extra core. And that's something very unique in the architecture for Azure Sphere. All right, any questions so far? All right, you're all with me. Good. Okay. Or asleep. Okay. All right, so let's talk about Pluton in a little bit more detail. This is what the fabric for Pluton looks like. And let me I should talk about the origin of Pluton just briefly. So Pluton is actually the secure processor that is used in the Xbox One and the later Xbox consoles. So this was developed at Microsoft. All the RTL was written at Microsoft. You may not know this. We have about 500 silicon engineers that work at Microsoft. Okay, they build like the HoloLens chips and the Xbox chips. And entirely RTL that was written custom by Microsoft. It's got some normal things you'd expect to see in a security processor. It's got some crypto engines. It's got a random number generator. A public key engine, ECC engine and RAM that's used for that. It also there's a full core there. It's a Cortex-M core on this implementation where we run the Pluton runtime in the secure RAM. So it's got its own private RAM where that Pluton runtime runs, and the secure ROM is the boot ROM for the entire system. And then the thing that's kind of pretty clever, okay, so the keys get stored. So every device, there's a couple of keys you have to have. So you have a private key, which is the device's identity. So in other words, when this device comes in to talk to Starbucks and says, hey, I'm a Starbucks espresso machine, Starbucks really wants to know it's one of their espresso machines. And it's not, say, instead, I don't know, a Pete's Coffee espresso machine pretending to be a Starbucks machine so that it can steal the pumpkin spice latte recipe, okay? Or the Pete's Starbucks machine, or the Pete's espresso machine that's feeding in wrong data to tell us that our machine learning, to pollute our machine learning model. Okay, so there's a lot of reasons why you really want to know device to device. So you got a private key for that. You have a public key. You've got a couple of public keys of which code am I allowed to boot and load. So the root of the secure trust. And the operation engine, think of it as a macro operator that does things. It will do, for example, the attestation. And so, and this is a sparse interconnect on the bus. And the reason this is a sparse interconnect is because in a secure environment, you don't want to allow every possible operation. So, for example, you don't want to allow the private key for the device to get loaded and then send out over the memory interface over to the CPU. Because you don't want anybody to ever be able to steal that. Even if somebody hacks the Linux kernel, I don't want them to be able to steal the device's private key and impersonate it. Or rewrite the public key that's the boot key, for example. And so we put they come into the key store over here with the cryptographic engine. And then when I say I want to do signing for attestation, let me basically describe what attestation looks like in practice. So as you bring up boot the chip, so you start off with ROM, and then you load what's called the BL1, the first part of the bootloader, and then you load the main bootloader, and then you load the secure world, the security monitor, and then the security monitor loads the kernel. Think about this step going up, and then the kernel loads an app on top of it. At each step, you collect a hash, and the hashes get put in a log, and a cryptographic hash gets made across those hashes as well. So you've got a measurement, and that tells me what is running on that device. Okay, and then when the device talks to the Azure Sphere Cloud and says, "Hey, I'm an Azure Sphere chip," the first thing we say is, "Are you sure?" Okay, so prove it, and the server creates a nonce. Do we know what a nonce is? Okay, we know what a nonce is. Great. Okay, server creates a nonce, sends the nonce down to the chip, down to the OS. The OS hands it all the way down through the software stack to the Pluton core, and the Pluton core hands it to the cryptographic operation engine and says, "Here's a nonce. Give me a cryptographically signed blob that I can give back to the server to prove that I am running Azure Sphere code, that I'm a legitimate Azure Sphere chip, running Azure Sphere code, and that it's this code that I'm running." And that all happens, and that operation, the set of operations around that all get done inside the cryptographic operation engine. And guess what? No software ever sees the key, which means no software can ever steal the key, okay, or corrupt the key. And in fact, we use formal methods. The cryptographic engine, Pluton, has been formally verified to make sure that no key ever ends up in the wrong place, and also formally verified that there's no side channel attacks to leak the keys. Okay, so that formal stuff really does work, and we really do use it. Okay, so that's Pluton. Any questions about Pluton? Yes. How do you formally verify like a power attack on a side channel? I have no idea. Okay, I'm just an OS wonk. Yeah, I have no idea. There are ways of doing it. I don't know. Probably, I don't know. I honestly have no idea. Okay, anybody want to try to ask a question I might know? All right. Oh, okay. So the question is basically, do we know all the private keys for the devices, for example? Or, yeah. Okay, well, let me explain how. Okay, let's talk about manufacturing really quickly. Thank you. This I know about. Okay. So one of the, okay, so where did the private key come from? The device's private key. How do you get a private key? How do we know who the private key is? That happens in the factory. So one of the unique designs aspects of Pluton. So we use ECC keys, all right, so the elliptical curve keys. And one of the primary reasons we use ECC keys, there's two benefits of ECC keys. One, compared to an RSA key, they're much smaller for the same cryptographic strength. The other one is to generate an ECC key, you need a source of randomization that you trust, okay? I'll come back to that, trust in a minute. And that's it. Okay, and it's pretty easy to generate a key. Whereas with an RSA key, remember with RSA, you've got to have prime numbers. And so it takes a lot of time to generate those sets of prime numbers. And why do we care? Because what we want to be able to do is manufacture these chips in very large volumes in a factory and not have it take very long in the factory to have them create their own key. And so when you manufacture chips, they come out as wafer. You get a wafer. And there's a test harness that drops onto the wafer and with probes and runs the probes to verify that the gates are all intact inside the chip. And this is before you even put it in a package. It also, in the case of the sphere chip, it tells it, okay, we're about to lock you down, generate your private key. And the chip generates its private key, locks itself so that nothing can have access to the private key and the private key can't be changed. And then it passes out through the test harness the public key that corresponds to it. And we collect that, connect to the Azure Sphere Security Service and say, okay, we just manufactured chip number 35, here's its public key. And so we now have established trust with it, okay? And most importantly, Microsoft never knows the private key. The only entity in the universe that knows this private key is that chip. And the only thing that can access it is the cryptographic engine, or you could acid wash it and read the fuses underneath, and that's a really costly and expensive thing to attack, and only gives you one key anyway. Yes, question? So what's the difference between Pluton and traditional TPM? There's some okay, let me put it this way. There's no secret sauce here. Okay, Pluton is not this, oh my gosh, everybody needs to buy Pluton. What's great, the value of Pluton is that it's just proven. We put it in the Xbox, and let me tell you, people really attack the Xbox. And so we have pretty high confidence from that. And so it's just some crypto engines. The cryptographic operation engine is unique, but it's an optimization. A TPM is off on the side, which means it's on a separate chip, which means you've got buses, an LPC bus. And LPC buses are pretty easy to attack. So it's much more susceptible to a physical attack, whereas this isn't because it's inside. There's some protocol differences, but it's kind of, 6 of one, half of a dozen of another. Okay, it's just a really nice packaging. You should think of it that way. Okay. Yes. Yeah, we actually do have a process. So the question is, do we keep track of which customer is associated with which public key? We actually do from this perspective. My customer, not the OEM's customer. So when an OEM, device manufacturer, when they take an Azure Sphere chip and put it into their chip, there's a process we call claiming. They will communicate with Microsoft, with our security service, say, hey, this chip is no longer just a raw bare chip. It's now a dishwasher model 33, for example. And here's the public key that corresponds. And so we do that. And we do that so that when this chip comes and asks for a software update, that we give it the Dishwasher 33 software and not the Launch the Nuclear Missile software, or vice versa. Okay, and so it really does matter, and we want to make sure we do that. One last thing, did everybody notice the environmental sensors up here? Why do you think we have environmental sensors in this thing? Any guess? For tamper resistance. Yep, actually, close. So it's for tampering in the factory. Okay, because it turns out we've got an entropy source down here, and entropy sources can be manipulated if you manipulate the temperature of the factory, for example. If you raise it up a lot or lower it a lot, you can skew the the source, the random number generator source, and so it's like all ones, your key's all ones, and you know enough to know that that's not really a great idea. And so we have environmental sensors that check to make sure, are we at the right operating temperature to be generating a key? Do we have the right voltage to be generating a key? And that. And then there's some checks on the random number generator to make sure that, well, okay, you really can't really tell it's a pure random number, obviously, but you can tell statistically the bit stream coming out of this, does it look like a random number generator? And if any of those fails, the chip just refuses to generate a key. Okay, thanks. Great questions. Let's move on here. Okay, so the security service, talked about that. So it does three key things. It does the remote updates. It does the remote attestation. So it collects errors from the devices. Let's talk about these in a little. So let's talk about the protocols that we use, and these are pretty important. So there's a couple, so there's some key things. So start off with server authentication. So one of the things you want to do is when a device, the dishwasher, goes and talks to the cloud, it wants to know, hey, am I really talking to the right cloud? And we just use standard techniques here. We use TLS for the encryption. We do server authentication of the certificates. One of the things we do, in the factory is we put in a base public key for Microsoft to say, hey, this is the key that should be used to sign the bootloader, for example. And then later on, as we do the claiming, we put on public keys for the device manufacturer. Okay, so it's just standard protocols right there. The next one is the secure boot. For the secure boot, you really want to verify that you've got the right software that you're loading, and we use ECDSA, which is pretty common secure boot protocol. Just uses ECC and the public keys on the device. And the key thing is we do have to burn one public key into the chip, which is this root bootloader public key. We only use it for the bootloader. You might ask, why just the bootloader? Why don't we use it for everything else? And the reason why is because you can't revoke that key. It's out on the device. It's burned into fuses, and we can't modify a fuse once it's blown. You can never unblow it. And so we use it just for the bootloader. The private key that corresponds to it is literally maintained in a vault at Microsoft. So when we sign a new bootloader, on the rare occasion that we have to do that, two people have to go to the vault and do. There's a bunch of complicated protocols. We use basically the same trust storage for the keys for Azure Sphere bootloader that are used for Windows PCs, for example. Okay, and then for device authentication, we use TLS here, but we use client-side TLS. The mutually authenticated TLS. So let me walk through the basic sequence. I wish I should have made a chart for this. It would have been a lot simpler. Apologize. Okay, so chip boots up. And you've booted all the way into the operating system. You did the secure boot. Everything's hunky-dory. And the first thing the chip does is it goes to the Azure Sphere Security Service and says, hey, I'm an Azure Sphere chip. And the security service says, prove it to me. And we do the dance where it sends down the nonce, and we get the signed blob, hands it back up to the security service. The security service says, yep, you are in fact an Azure Sphere chip. Well, there's three possibilities actually that can happen here. The first one is it can say, oh, your certificate doesn't match. You signed it, between the nonce and the measurements, you don't have a valid value. Okay, in which case the chip reboots itself. Okay, because something got corrupted along the path, and the only thing we can do at that point is, well, let's just reboot and try again. Okay, and maybe fail over to an old version of the OS if we have to, if something's become corrupted. So it's, you have to deal with it locally. Second thing that can happen is we can say, oh, you are in fact an Azure Sphere chip, but you are running out-of-date software. Okay, and if you're running out-of-date software, what I'll do is I'll give you, it hands back a certificate that can only be used to talk to our update servers. And so then we'll go do TLS and talk to the update servers and say, hey, I've got a certificate that proves I'm a legitimate Azure Sphere chip. You need to give me the latest software, do an update, et cetera. And then the third case is you're running the right software, in which case we now give you a certificate. Now, one of the things you should know, I assume you guys covered, public key infrastructure is really hard to get right and really expensive and dealing with expired certificates and everything else. And we just made a shortcut. We said, you know what? We're not gonna revoke keys, or we're not gonna revoke certificates. What we're gonna do is have our certificates only be valid for 24 hours. So you do this dance and you get a certificate that you can only use to talk to servers for 24 hours. And after 24 hours, if you still want to talk, you have to come back again and prove that you've got the right software and everything else. And so that's how we dealt with that. Okay. All right. Okay, 55, right? Okay, I was thinking 35. Oh, sorry, folks, you almost all got out of here 20 minutes early. Okay, all right. So let's talk about some of the practices. Let's see, actually, before I go, any questions before I move on? Okay, I need a drink. Yeah. Okay. So the question is, how does it know which server, when a chip boots up, how does it know which servers it should talk to in the Azure cloud? And the answer is, yeah, it's a DNS name. So we have DNS name. It's basically, it's like azureспhere.something.microsoft.com. Okay, and let's see. One of the things you might ask as well is, well, what if like my certificates of my change? Oh, actually, I'm not going to go into detail on that question. Yes, DNS. Okay. All right. So the paper that you got pointed to talks about 19 of just kind of the best practices that we built into Azure Sphere. I'll be really kind of blunt. I would call this a vanity operating system project. Okay. And what I mean by that is every place my engineers could figure out some place that they could do a tweak that made a little bit better security, they pretty much did. It was like carte blanche to add security features. Do you really have to have every single one of these in a device? No, I don't think you do. Okay, but I'll talk about. But it's kind of like an embodiment of a lot of really good best practices, and so that's why I'll kind of walk through these things. Okay, and what I'm going to do, I am not going to drag you through all 19. Okay, I'm going to hit about 4 out of the 19. And if there's one that you said, oh, but I really, really wanted to know about never exposing private keys, then you'll have to ask, and I'll answer that question, okay? All right, but overall, the top. So treating the ROM as non-updatable software and minimizing its code. Basically, you want to make your ROM as small as you possibly can because you can't fix it. Whatever bug is in the ROM, the only way you can fix that is to spin a new version of the chip. Now, luckily, it's what they call a metal spin. It's just the top layer of the chip that has to be respun. We did actually have to do a metal spin on the MT3620. The very first version of it was susceptible to glitching attacks. Have you covered glitching attacks in here? All right, let's talk about glitching attacks. Okay, so you all know about processors. They execute the instructions that you tell them to execute in a very methodical, predictive, deterministic manner, right? Okay? Except what happens if right halfway through executing your instruction, the power goes out? Okay, but the power doesn't go out enough for you to completely fall on the ground. Oh, and then I'm back, and I keep executing. That's called a glitch. Okay, and if you get a glitch halfway through an instruction cycle, what is the state of your processor? The answer is, who knows? Okay, and it is one of the best ways to, imagine you've got a bootloader, and the bootloader code looks like read, there's an iterative loop that loops through and reads all the bytes of the image that you're checking the signature on, and then does a compare. Okay, and a compare looks like, compare operation between, two values, the value it's supposed to match and the one that you just calculated, and then you have an if statement, and the branch, either branches go left if the check succeed or go right if it didn't. Well, what if you could skip the compare instruction, okay? And because of the sum instructions in front of that, the right flags were set on the processor so that the if always comes out to be true. True meaning the signature is valid. So all you have to do is eliminate that one instruction. If you can just make the processor not execute the compare instruction, then it will always say that your code is valid, okay? And that's what's called a glitching attack. And it takes about $10 of electronics to put together a small FPGA that pulls the power line at a deterministic time to cause you to skip an instruction, okay? Yes? Is it just like... Oh, Intel Thunderbolt. I don't know. Yeah, I don't know. There's been a bunch of glitching attacks against different things. Anyway, but our first version of our chip was susceptible to a glitching attack. Now, there's countermeasures. The way you do countermeasures about that is you basically put values into registers as you go along, and you don't just check that one place, the if. You also, later on, 1,000 cycles later, you double check, hey, did those two things really add up right? And if you do that enough places, and then you put in some randomization so that because it's really hard to be able to see from the outside what's going inside a chip. You basically just have to count from so many cycles after the reset pin was pulled. And so if you put in some randomization, it becomes a lot harder and some things. So anyway, but ROMs do have problems, and so you want to make that code as tight as possible. We don't expose the private device key. I talked about that quite a bit of detail. I talked already about why we use ECC. We use secure boot, basically just all the way up the stack. Every single layer checks the signatures on the next layer before it loads the next layer in. We use silicon-based measured boot. Okay, I talked about remote attestation already, how that works. And the other thing is parsing certificates. Let me tell you, everybody who has ever built a certificate parser has made a mistake. It's a terrible data structure format that the 509 certificates are used. And so one of the things we do is we just don't parse them in trusted code. So we have a parser that sits outside up in untrusted code that parses and then hands the key out of the certificate down in the lower layers, parsing the code. Okay. Okay, so that's that set. Let's see. I talked about measured boot quite a bit of detail already. I'm going to skip that. Handling the server certificate expiration gracefully. Let me see. What's this? So one of the scenarios we ran into with Azure Sphere, so it's pretty common, like on your PC or your phone, your TLS certificates that are used for you to talk to, Apple.com in TLS. Those certificates typically have a period of about 2 years, and then they roll them. You get it within about 6 months of the 2-year period, and you roll it to a new certificate, and you do that. And there's a lot of best practice about how you maintain certificates and roll certificates forward. Let's see, you guys might remember, about 10 years ago, no, you don't. You were all in elementary school, you don't remember. About 10 years ago, Azure went down on February 29th. Now, why would we go down on February 29th? Because the certificates all expired on February 28th, and the new certificates didn't start until March 1st, because nobody had thought about leap day being the day that the certificate expired. So it's a real pain. And there's a bunch of things you do with a device that you're connecting all the time to kind of maintain certificates. Now, we have devices, if you think about like that dishwasher that we were talking about, that dishwasher gets manufactured and then it gets put in a box and then the box gets sent out to a wholesaler, and eventually it gets put into a retailer, and eventually a retailer sells it to a construction company, and a construction company might put it in their warehouse for a while, and then eventually it gets, the house, because the house isn't done because there's some other thing that's, eventually like 2 years, 3 years, 4 years after it was manufactured, it might finally get connected to the internet. Oh, because maybe you as a consumer, you didn't connect it for a couple of years because you didn't even realize it could be connected, and then one day on a lark you were bored, so you connected the internet. Okay, guess what? All the certificates on that thing are expired. So what do? Well, we use HTTP, not HTTPS. We use HTTP because no need to check the certificates, and we go out and we talk to a well-known location and say, give me the new certificate blob, public key certificate blob for talking to Azure Sphere, and we bring it down. And what it does is it checks the signature on that blob. So it doesn't check the transport, because if there's a man in the middle, all that means is, well, reboot and try again, because that's all you can do. And so that's how we deal with certificates of servers for the booting. Okay. Okay, connectivity is optional. So one of the things we mandate is every Azure Sphere device has to work correctly without being connected to the internet. So your dishwasher has to run dishes even if it isn't connected to the internet. That seems pretty obvious. Botnets. Okay, so one of the things we're really worried about, and you see this with IoT devices, them getting turned into botnets. So the device gets reprogrammed. Somebody finds a hole in the application. They replace the application with the spam sending app or the botnet app to use it for a distributed denial of service. One of the ways we deal with this is every single app on Azure Sphere, at the time you compile and link your app, you also provide a manifest that lists which DNS endpoints you're allowed to talk to on the internet and which physical resources on the device that you're allowed to talk to. And so when we load the app onto the device, and we sign that, by the way. It's signed and comes down as part of the blob with the application. And so when the app tries to open up a socket, we look in the manifest and say, are you allowed to talk to this endpoint or not? And so you can't reprogram an app to, if the app's meant to go up to just Whirlpool's cloud, IoT cloud, because that's the only DNS point is iot.whirlpool.com. If it tries to go anyplace else on the network, it'll be blocked by the internal firewall. And so that's one way we deal with that. Okay. Okay. And then, deny by default. So every place in the chip, everything is denied by default. So, for example, no one gets access to any resource. You can't talk to any GPIO pins until you get permission to, etc. It's just a well-known good practice there. I talked about eliminating the concept of users and physical separation of real-time execution. I talked about that as well. All right. Let's see, that's that in detail. Okay, obviously dividing code into user mode and kernel mode is a good idea. Ensuring all the software is updatable. Everything in the stack is updatable by us, including all the way down to the 1BL. So the ROM is the only thing that we can't update on those devices, and it's all done in a deterministic, predictable manner. We keep 2 copies of every single piece of code. We have the last known good and the current update. And so when an update's applied, if anything fails in that update, like say you brought down some new code, but as you get it down and check the signatures, they fail, we have a last known so that we can fail back over on that. Let's see. Make software update fault tolerant. Yep. Isolate the apps so they're separately. Do not allow the system to dynamically change code execution. We don't allow jitting on these devices. All the code has to be statically compiled. And the other thing is we don't allow any dynamic modules in the kernel. We completely remove that capability as well. And it's basically, if you think about it, it's an embedded device. You know what the hardware capabilities are before you ship it, so you shouldn't be building in drivers that you don't need. And then the last 18 is the downgrade attacks. So one of the most common ways to attack a device is that the hackers use is, let's say Windows. So Windows releases a software patch. The hackers do this. They go disassemble the software patch, figure out, okay, what was the vulnerability they just fixed? And now, okay, I understand the vulnerability. Let me build an exploit that works against the old version of the software So one, I'll go attack machines that have the old version of the software. But also, if I can fool your device into loading, or you into loading the old version of the software, then I can attack you very, very easily. And so there's cases where, if there's, like we've discovered vulnerability, we don't want the software to be able to roll back. So we deal with that with two ways. If it's a higher level part of the stack, we just update the certificates. If it's down in the bootloader, that's a little more serious. What we have to do with the bootloader is we actually have fuses. And we blow a fuse. And you think of the fuse as basically encode so I have to have version 3 or greater of the bootloader. Or if I blow the next fuse, I now have to have version 4 or greater of the bootloader. And so we'll blow the fuses, and that's how we deal with that issue. Okay. And then the last thing is about really using the tools and the processes. So we do some things like our build system goes out and checks against CVEs, against all the pieces of the open source that we use to see if there's any there. We use software fuzz testing. I'm positive you guys have talked about fuzzing, right? We use fuzzing pretty extensively, both for our protocols and also for our kernel interfaces. We do a bunch of static analysis. We use both Microsoft tools and third-party static analysis tools, and we use red teams as well. Okay, and we have exceptionally good hackers at Microsoft because it turns out we like them and we pay them a lot of money, and they anyway. Like the glitching issue that I talked about, the glitching bug, that was found by one of our red teams. They found that. They got really frustrated. They couldn't find any software bugs, and so they started hacking the hardware. And the way we do this, we do 2 red team exercises every year against the OS and 2 red team exercises against the cloud. And the cloud, we have the red team we assume that they're already on the Microsoft network and have access to the Microsoft network and see how far they can get with access to the Microsoft network in terms of attacking the cloud. And those have been really super valuable things. Okay, so let's talk about the proof really quick. Actually, let me pause. Any more questions before I move on? Okay. All right, you're all thinking, if we don't ask any questions, we'll get through quicker. All right, so let's talk about what one of these red team exercises how we do. So we do both internal red team exercises and external ones, and the external ones are the funnest. So in 2020, we did an example. We do this about every 2 years. We do a 3-month security challenge, and we go out and we recruit a bunch of security experts from outside and security vendors. We go recruit them, and we get some great participation in this one. We had McAfee and Cisco Talos. The Cisco Talos guys are absolutely amazing hackers. FireEye, Avia, etc. And we say, hey, look, you come in, and we will offer you bounties. And if you find a bug, and the price, the bounty award goes up the farther down in the stack. So if you manage to break out of the app sandbox, I don't know, it's like $5,000 if you break out of the app sandbox. It's $25,000 if you get into the kernel. It's up $50,000 if you get into the security monitor, and $100,000 if you can find a vulnerability that gets you into the Pluton runtime. Okay? It turns out money motivates people. Okay? I don't know. We might offer them free T-shirts too. Okay, and we had some great. These were when we give them 90 days and go get after everything. By the way, we have a persistent bounty program. So if you go find a bug in Azure Sphere, a security vulnerability, we'll pay you money. Okay, this active program, we do it periodically. We also give them access to our people, by the way, too. So, we have every day we have a hotline, office hours that they can call in and ask questions. So we had, like I said, this time around, we had a total of 40 submissions. 30 of them were real issues, okay, were real potential security vulnerabilities. 10 of them were things that were, we know that. We designed it that way. It's doing what it's supposed to. That's not a security flaw. And we ended up paying a total of $374,000. Money well spent. 48,000 was the largest. Nobody got into. There was one 0-day. So McAfee and Cisco both found 0-day Linux vulnerabilities, But even with that, even with kernel root access on the device, they were not able to get any further down into it. And the other thing is, we fixed these. We were pretty serious. I mean, it's not just that we are out recruiting. It's like every single day, as soon as a vulnerability gets brought to us, we've got a team that's ready to, okay, how do we fix this? How do we address this? And so we had everything fixed within 30 days. And the next release, before any of this was published, everything was updated out on the device. So we've never had anything that we'd recognize as a 0-day yet. Okay, we've never had yet anything that I'd recognize as a 0-day on the device. Okay. And I thought you might be interested in, okay, so McAfee did a fantastic job. What kind of things did they do? Well, they really became experts in our product. They read all of our documentation. They read everything we could find. They went out and trolled the internet for videos of our team speaking at conferences or like the Linux conference and stuff. They reversed engineer all of our code. I don't remember how they did it, but they got the ROM off the device and reverse engineered the ROM code. They went through, and they used multiple teams. They split up to do that, and they went everywhere. The network stack, having a rogue app, trying to get out of the sandbox. They tried attacking our signature verification stuff. We have a dev experience where you use Visual Studio or VS Code to talk to the device and program it. They tried breaking that connection, went through the drivers, all sorts of, every place, up and down. And, they used pretty much everything they could come up with in terms of looking at the raw blobs and fuzzing our blobs and everything else. And, like I said, the rogue apps as well. Okay, so they went really, really thoroughly and really, really deep, and that's fantastic. Anyway, okay, that is the end of my discourse. Any more questions? Yes? Yeah, okay, so the question was, okay, so we write in, this stuff was all written in C and C++, so we thought about going into other languages, like using Rust, for example. Or, let's see, you mentioned Cherry, too. Cherry's about hardware, right? By the way, I love Cherry. Have you guys talked about Cherry in here yet? You should talk about Cherry. It's good stuff. Cherry's some extensions that were developed at Cambridge University with ARM for doing a bunch of safety checking in code. It's really great work. We've got some stuff going on in Rust right now. I will say this. I am a Rust skeptic. And the reason why, I build an operating system called Singularity. If you take an OS class, you may not hear about it, in which we wrote the entire thing. Well, we tried to write the entire thing in safe languages, a C# language, and we used linear types. And all I will say about linear types is they're a pain in the butt. Okay, like go try to build a doubly linked list with a linear type. You can't do it. And go look and see how many doubly linked lists there are in your operating system. And the answer is quite a few. And so it was really, really challenging. And Rust has linear types. They've done some stuff to improve. And I guess I'll say this. I don't have a lot of experience. But I'm skeptical. I'm hoping to see if they come up with some better ways of dealing with linear types than we did when we built Singularity. But we are doing some exploration there. And some other things, kind of higher level languages as well. So, okay. Yes? Do I think it's infeasible to secure IoT devices just with software? So, for example, if we had the operating system but we didn't have the hardware root of trust?
Or like if we didn't need to put a chip inside at the manufacturer.
Oh, if we didn't need to put a chip inside. You've got to have a hardware root of trust. And here's the way I'll describe it, at least of some form. And the way to describe it is, if you don't have a way of protecting the device's identity, no amount of software can protect it, okay? And so you've got to have at least some. Do you have to have everything that we have in Pluton? No, I don't think so, okay? But you do have to have at least, the basis for secure boot. So the hardware at least has to somehow not load software that doesn't have some kind of a signature, and you really should have some way to protect a private key on the device. It's kind of what I think is the minimum you have to have a software. our hardware. Yes?
Yeah, I can imagine how valuable the hacking exercises were so that you went right after. But what about all the exercises that you protect against? Do you use those as some form of unit test before you ship a product?
Oh, okay. So the question is, so of all this hacking, the ones that are successful, we're able to fix. The ones that aren't, where they failed, do we use it as a test, as, for example, unit test? That's a good question. I don't know that we do it systematically, okay? But I do know there are quite a few places where the vulnerabilities, once we've found one and fixed one, we do put checks in. And the most important thing, with a vulnerability is, my assumption is if you make a mistake, you're going to make the same mistake a second time. So so you go look. So whatever the error is, you look and see what is the pattern. Now, how do we look across the entire system for that pattern? And so that's a good reason. You can figure out a test that tests for a pattern, you leave that test in there. Because if you made that mistake once, the odds of you making it again are definitely non-zero. And so we do that. Yes? Hold on, let me come a little closer. Okay, why do we run the separate code on the real-time code? And what was the second? Oh, and why the firewall's there? Okay, so we run the. Okay, so I'll go back to the example of the stoplight. I want to build this traffic light that is a highly secure, connected, smart stop traffic light. Okay, the real-time loop around around that is pretty simple. Okay. And the validation checking that, that has the light been on long enough before I turn it off, those kind of checks, are all the lights, are at least half the lights red, and the right one's red while the other ones are green. Those are really easy checks to write and put in the real-time code. And the thing is, we don't want any place else in the system to be able to prevent that. Actually, let me give you an even better example. One of the appliance manufacturers that we worked with when early on in our experience with them, they did an audit of their existing appliances. And they found that they had a gas range, that they had a gas oven, stove, I can never remember, the one that the fire comes out the top, okay, that you could remotely turn on the gas. That was one operation. And then there's a separate operation of remotely turn on the lighter. Anybody think that's a good idea? Okay, of course not, right? It's like, hey, you want to blow up your house? Okay? But they had it, okay? And so, that's a real-time check. You want that check that, if the gas goes on within so many seconds or, milliseconds, that the either lighter goes on or the gas goes off. You want that in the real-time code. Okay, and you don't want an interrupt to interfere with that. You don't want a network packet. You don't want anything to interfere with that. And you don't want anybody able to hack it and interfere with that. And so that's why we put that over on the real-time core. The reason we put the firewalls around the real-time core is if somebody did manage to corrupt. We have multiple real-time cores, and they can be used for lots of different things. And somebody could use one for something that's a non-trusted operation, and we don't want it to somehow be corrupted and be able to come back in and attack the rest of the system. So that's why we put those firewalls around the real-time core. Do you have to have? I could see situations where you say, really, I don't care if the safety code goes and kills the kernel on the main OS. I don't care that. I can see making a case for that, but that's why we did it. Okay. All right. Any other questions? All right, well, thank you all. Oh, one more question. Oh, man, you blew it. Everybody's going to leave. Just kidding.
How difficult is it for the end developers to integrate with this? Do they have to do anything special, or can I just develop anything that runs on an ARM7 and hand it to you and it just works?
Oh, super good question. So how hard is this to develop? This added security, does it cost a lot of extra effort, for example, to developers? Basically, the effective model is if you have some code running on Linux, you pretty much can just drop it in and it'll run. I mean, depends on what dependencies you have. If you've got libraries that we don't support, that's a problem. But mostly you can just bring it in, and then the only thing else you have to do is build a manifest. So, say, oh, here's the network connections my code's supposed to be able to use. Here's the hardware connections that I'm supposed to use. And our hypothesis is, you should know those things, right? You should know where you're trying to connect to, and you should know what hardware you're talking to, and that's... So our experience is it's not been too bad. We've had some glowing reviews from some of our developers of, they've been on embedded Linux environments or on real-time RTOS environments, and they come in here, and they think it's pretty fantastic. We spent a lot of time on the developer tools. One of my hypotheses when I started Azure Sphere was that, I assert Microsoft has two superpowers. One of them is security. We really passionately care about it and done a lot on it. And the other one is productivity. And so we tried to bring both of those to bear on the system. Thanks for letting me make the plug, by the way. Okay. Yes? Oh, yeah. Okay. So, yeah. So the point is, this looks like it's expensive. It is on the expensive side. And, are we trying to do anything for like cheaper devices? Probably the way I'll describe it, we're actually going more expensive. I'll describe it this way. I thought we were going to try to go after the entire MCU market when we did this, which would be, things running on a AA battery with a sensor stuff. And I hope somebody does, but what we really found is, because of our business models and things at Microsoft, really are most effective is devices that go into enterprises because they need cloud services. And also, let's say I didn't talk in here. Basically, there's a Moore's Law curve thing. MCUs use the cheapest silicon manufacturing processes they could possibly find. Which traditionally has meant they're way, way behind Moore's Law than everything else and move very, very slowly forward. But the thing that's happened that, it's moved much more rapidly than I anticipated is iPhone. iPhone uses a huge amount of silicon every year, okay, at the latest process technology. And next year, they want to be on next year's process technology. So that means all the fabs that were built this year to build this year's iPhone next year are looking for a customer for something to do. And so as a result, it's basically sucked the entire MCU market really, really fast. So I'll give you an example. Like we have, literally a dishwasher manufacturer that when we started talking to them about Azure Sphere, 4 years ago, about, hey, this is a chip with 4 megabytes of RAM. They were on a chip that was 512K of RAM. And we said, we want you to use this one with 4 megabytes. I was like, wow, what would we ever do with 4 megabytes of RAM? Well, their next generation is a chip that's got 256 megabytes of RAM, okay, and a gigabit of flight. And they're using Docker containers in their dishwasher, okay? And you're like, what the heck? Why are you using Docker containers? Well, they're using Docker containers because then they can have two separate teams. One team that's writing the code that programs the LCD, and another one that's running some other piece of code. And they don't have to use the same library versions, okay? It's like madness, okay? But and why did that happen? Because the price just dropped so quick on the processing power. So anyway, so I call me greedy. I follow the money, okay? Is there still a market there? Yes. If you want to go do a startup that figures out how to really do it for really cheap, go do it. And my one piece of advice, if you do that, is use Cherry, okay? All right. Any other questions? Did you go? Oh, yeah. So the question is, okay, it looks like we have to redo the certificate every 24 hours as long as we're talking, and isn't that expensive? And can we really afford to do that? It turns out it's actually pretty low bandwidth and pretty low computation because it's mostly happening over on this crypto engine, okay? So it's not much power and it's not much thing. But we've definitely had some discussions with people about maybe doing some longer time. It's high order bit, it's not as bad as you think it might be, okay? Particularly when you think about, okay, I only need it if I'm going to communicate. And if I'm going to communicate, I'm going to be using TLS anyway. I'm going to be doing certificates and all that. And, in terms of raw cycles, that's a lot. It's basically, it's like, you kind of go 2x for the overhead of setting up a socket. It's kind of the way to think about it. Okay. Yes?
There's a device with the chip and one without. What's the difference in power usage? Have you been able to observe if they monitor electricity on?
Okay, so a device using Azure Sphere versus one node, is there a difference in the power? Have we measured, like, looking at the power? No, we haven't measured it, okay? And I guess probably the way I'll say it is either people really care about, either they want Azure Sphere and they'll figure out how to, yeah, okay, it's a little bit power. The big thing is mostly that you're running a Linux kernel, okay? There's kind of a base of, and you've got this much RAM that you've got to power. And that actually is kind of, the primary power costs are booting Linux, and that we add booting Linux and then the RAM to hold that. And for anybody that's using embedded Linux anyway, it's a wash. Using Azure Sphere versus not using Azure Sphere is completely wash in terms of power. If you're coming from some really low-end microcontroller, it's a lot of power. Okay, I will say that. I know it's a lot of power, and so we've had people look at it. And this is kind of back to that question about money. It's like I could go spend a lot of engineers working on the power, and there's other ways to attack that problem. So one of them we're looking at is like setting up so like the real-time cores can be running without ever booting the Azure Sphere side, the secure side, the rest of the chip until you need it, and then to bring it up, for example. Anyway, okay. Any other questions? All right. Well, thank you very much. Appreciate your time.